Guys, let's compare Bernoulli and Markov chain run lengths as we finish off our foray into the land of conditional probability and the Markov chain. It's a very interesting way to finish, so I hope you'll enjoy it. Now, the number of times that the same outcome is observed in sequence is called the run length, or the length of the run for that particular sequence, okay? For a Bernoulli trial, if we have an event of low probability, the probability of a sequence of n successes in a row that is, before the first failure is much, much lower than for an event of high probability. Now that makes sense, doesn't it? We'll have a look at an example just to make sure we understand this. If the probability of success was, say, 0.9, then the probability of 5 successes in a row would be 0.9 to the 5, would it not? Yes, and that would be 0.5905 to 4 decimal places. And if the probability of success was 0.1 at the other end of the spectrum, then the probability of 5 successes in a row would be 0.1 to the 5, which would be very low, 0.401. So you see what I'm saying, okay? For an event of low probability, the probability of a sequence of n successes in a row before the first failure is very, very much lower. So you're not likely to get a decent sized run length of successes in a very low probability event. But you've got quite a reasonable show of getting that for a high probability event. That's all we're saying, all right? That makes sense, doesn't it? Now, for Markov chains, this is not necessarily the case, not at all. Because the probabilities at each step are conditional probabilities, it actually follows that for a two-state chain, which is what we're dealing with, long run lengths of both outcomes might be observed, okay? And we're going to demonstrate that in this video. But in the process, we'll get to do plenty of computations of Bernoulli run lengths and also Markov run lengths of the same outcome in succession, so you'll get to know how to do that without any shadow of a doubt, and that'll be very good too. So there's really a spin-off benefit of this video in enabling us to know how to do that with certainty and confidence. Now, what's this? Find the probability that a fair die will need to be rolled 5 times before a 6 is observed on the 6th roll. Okay, well that's a Bernoulli, isn't it? Definitely a Bernoulli. So let's say the probability of getting a 6 is 1/6, okay, and the probability of getting everything else is 5/6, okay? So we're saying we want a run length of 5 of these before that's a success, before we get that, which is our failure, our first failure, okay? So the probability required is going to be 5/6 to the 1, 2, 3, 4, 5 for the 5 successes times the 1/6 for the failure when we roll a 6, okay? Do you understand? So that's how you do a run length for Bernoulli. Very, very simple, isn't it? Yes, run length of anything but a 6, 5 of them, followed by the getting the 6, which is 1/6, yeah? So what would that come to? That would come to 0.0670, okay? There you go. That is the probability of that scenario, okay? That is a Bernoulli trial with a run length of 5, isn't it? Run length of 5, that's the length of the run of the same outcome, okay? The same outcome before we bite the dust and get the failure which stops our momentum. Yep. Okay, now, suppose that a biased coin where the probability of getting a head is 0.9 is tossed, okay? Find the probability that 3 heads in a row are observed before a tail and all those other scenarios. Let's just do A first. Won't bite off more than we can chew. So that what we're looking for here is the probability of head, 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 tail, right? That's head and head and head and tail. And the and directs us to multiply these probabilities together because it's a compound event of 4 parts each, and this and that and that. Yeah, so you multiply the component probabilities together and that's a run length of 3, and what do you get? 0.0729. Okay, that's that one. Now let's see what B is. Yes, a Bernoulli trial run length 3, we know that. Thank you, Mr. Computer, for telling us. Now B, 6 heads in a row. Oh goodness, that's going to be a low probability, isn't it? Good heavens above. Let's try that one. There it is. So that's 1, 2, 3, 4, 5, 6 heads and then a tail. 0.9 to the 6th times 0.1, and our run length is 6. Bernoulli trial run length of 6, and that's going to be 0.0531. Woohoo! Okay, very, very interesting, isn't it? Now let's do C. 3 tails in a row are observed before a head. Okay, now we're doing, I see, we're putting the boot on the other foot here. We had 3 heads in a row before a tail. Now we're doing 3 tails in a row before a head. So this is going to contrast the low probability run length with the high probability run length up here. You see, we should get a minuscule value for part C, I would think. There it goes, and it's it's minuscule, all right. Very, very low compared to this one up here, yeah? You see that? That's 3 low probability events in a row, run length of 3. This is 3 high probability events in a row, run length of 3, okay? So that's what that is. Yes, yes, we get that. Now, part D is 6 tails in a row. That'll be very extremely low because that's a run length of 6 of a low probability event in a Bernoulli trial situation. And yes, I thought so. It's absolutely infinitesimal, isn't it? 1, 2, 3, 4, 5, 6 zeros, 9. Okay, well that demonstrates the point, doesn't it, guys? That a run length of a high probability event of significance, such as 3 or 6, is much, much more probable than getting the same run lengths of the correspondingly low probability event, isn't it? Yeah, and that's what we said at the preamble to the video. Yeah, Bernoulli trial run length 6. Thank you, Mr. Computer, for keeping me on track. Now, so the difference between probabilities of equal length runs in A and C, that's this one, high probability, low probability, run length 3, and again in B and D, so that was high probability, run length 6, low probability, run length 6, is dramatic. It certainly is dramatic. Yes, it's dramatic, as would be expected, because the probability of success in A and B was 0.9, and the probability of success in C and D, is 0.1 for a Bernoulli trial or situation. So what do we got here? We have a Markov chain defined by the transition matrix. Right, okay, what is this? Wet and dry, okay, the weather looks like. So this is wet given wet the previous day, yes. This is dry given wet the previous day. This is wet given dry the previous day, and dry given dry the previous day. That's a transition matrix if ever I saw one. That is it, right? So WI is the event day I is wet, DI is the event day I is dry. What is the probability of that? Given that the first day is dry, there will be a run of 4 wet days in a row before the next dry day, and this looks like the reverse situation. There will be a run of 4 more dry days in a row before the next wet day. Okay, now let's see how we go with this, because according to the preamble at the start of the video, with Markov chain situations of 2-state chains, which we have here, either wet or dry, the probabilities of run lengths of opposing events is not necessarily dramatically different. Okay, so let's see how it works out. Oh, now what's this? That's what are we saying? There's going to be a run of 4 wet days in a row before the next dry day. All right, so the probability of that is the probability of dry on day 1. Now I think they told us, given that the first day is dry, well that's going to be a probability of 1. Now, okay, so we've got 4 wets in a row, okay? So wet 2 given dry 1 times wet 3 given wet 2, because that was a wet, times probability of wet 4 given wet 3 times probability of wet 5 given wet 4. Then the next one, which breaks the drought, is the probability of dry 6 given wet 5. Now that takes a bit of head power, and you've got to really keep your head together while you're doing that, and to make sure that you don't go wrong, okay? I mean, you know, there's a blizzard of data there, guys, so you just have to be careful. So keep your head and be cool, okay? So that's 1. Now, what was this? Wet given dry. Is that right? Wet given dry, yes. What's this one? Dry, wet given wet. Okay, where's wet given wet? Yes. Oh, very nice. That's that one, that one, that one, and that one. And the last one was dry given wet, wasn't it? Now, where's that? Yes, I think we're in business. I think it's right. Okay, now what does it come out to? Roll the drums. Ooh, 0.0316. Now, what is that again? It's the probability that there will be a run of 4 wet days in a row before the next dry day, okay, given that it was dry on the first day. Yeah, very interesting, isn't it? Now, let's see how the other one goes if we get a similar figure to this, right? Let's see. So B, yes, a Markov chain, run length 4, yes, we know what to do, and we know how to do them now, don't we, guys? Yes, you've been looking and you've been observing. That's how you do run lengths with Markov chains, okay? With specific outcomes every day in the sequence, yes? Good show. Now, what's this one? Goodness, more blizzards of data. Okay, so the probability, what are we doing here? Run of 4 more dry days in a row before the next wet day. Okay, there's day 1. So we've got dry 2 given dry 1, and then another one, and then another one, and then another one, and then we break the drought with a wet day given on day 6 given dry 5. Okay, so now we've got to plug all this in. That's a 1. Let's just, yeah, here we go. That's 1. Now, hang on, what's dry given dry? I've got to make sure we get this right. Yes, that's pretty simple. Okay, so 4 of those, 1, 2, 3, 4, and then a wet given dry. Where is a wet given dry? There it is. Yes, yes, this looks good. This looks good. Okay, and let's see what that comes. Oh, yes, it's quite similar. It's quite similar. It's certainly in the same ballpark. It's only about a factor of 2 different from this one up here. I think what this really proves is that it's just the probabilities of opposing events with Markov chains can work out to be quite similar. Okay, they can be quite similar. Because if you look here, you've got lots of 0.7-ish ballpark stuff happening here with a 0.3, and down here, that was with the run of wet days. Down here with the run of dry days, you've still got runs of 0.7-ish kind of things happening here. See, that's the influence of this one here in the first instance here, and then you've got this one here in the second instance here. Okay, so they can work out quite similar. I think that's what we're really trying to say. Okay, now in contrast to the previous Bernoulli trial, the probabilities of 4 wet day runs and 4 dry day runs is similar because of the conditional probabilities and the way they determine the outcome. Yeah, I think that's fair enough. Do you agree? Yeah. Now, what have we got here? Suppose that the probability that an operating machine breaks down by the end of the day is 0.10, and the probability that a broken machine is repaired by the end of the day is 0.55. Okay, find the probability that a machine that breaks down on day 0 will be not working until day 5. Okay, will be broken down until, I presume that means the end of day 5. We'll have to look at that in a moment. The probability that a machine in B, the probability that a machine that is working on day 0 will break down for the first time on day 5. Alright, well that seems reasonable, doesn't it? So let B denote broken down and let W denote working. Okay, now let's get some terminology right here. So B given W denotes broken down at the end of the day. That's the way I interpret it, given that it was working at the start of the day. Okay, I think that's important to articulate that, otherwise you can get yourself into a very big knot trying to work these things through, these worded questions. Now, also W given B denotes working at the end of the day, given that it was broken down at the start of the day. Now, I'm coming up with a transition matrix here. Now, this is the end of the day. That's the sort of the present. This is the start of the day, the given, what went before, okay? And it's working, broken, right? And you can do your street directory kind of reference, map reference thing here to intersect these points to work out which of these 4 items is which, yes, within the matrix. Now, alright, so we better fill in the numbers, okay? So it's saying here that the probability of a machine which is broken down at the end of the day, given that it was working at the start of the day, was 0.1. Let's see if that makes sense. Probably obviously breaks down by the end of the day. Yes, that's right, given that it was working at the start of the day. Therefore, this little baby up here has got to be 0.9, doesn't it? Yeah, because they've got to add up to 1. And also we're saying here, this one here is 0.55. That is the probability that a broken machine is repaired by the end of the day. So working, was that right? So yes, that was broken at the start of the day, working by the end of the day. That's right, I've got it right. Okay, you get your head into a bit of a spin with some of this stuff. You just got to keep your cool and go for it, and you'll be okay. And that therefore must be 0.45 because these have got to add up to 1. Okay, so there's our transition matrix. Oh wow, we're looking good now. So the probability that a machine that breaks down on day 0 will not be working until, I presume that means the end of day 5. Okay, so the probability required is a probability of broken down at the start, okay, times the probability of broken down on by the end of day 1, times the probability of broken down at the end of day 2, probability that it's broken at the end of day 3, probability it's broken by the end of day 4, times the probability that it's working by the end of day 5, given that it was broken at the end of day 4. Alright, I think that makes sense. Yes. So okay, that's a certainty because it was broken at the end of day 0. Now, does this make sense? Broken, given, broken. Yes. 4 of them. Oh, this is a piece of cake. Are you happy with that? I'm pretty thrilled with it. Now, what does it come out to be? Goodness, it looks like a big mess, doesn't it? 0.0226. Okay, what about, yes, Markov chain run length, that's right, 1, 2, 3, 4, before we finally break the drought, yeah? Very good. Okay, B for you and me, the probability that the machine that is working on day 0 will break down for the first time on day 5. Okay, so we've got to account for every day, don't we? Yes? So it's a run length one, isn't it? Yes, I think it is. So therefore, what have we got here? Our transition matrix was that, wasn't it? Yeah, from before. So the probability required is, let's set our run length down. That's the probability that it's, what was it? Was working on day 0, yes. Times working, yes, at the end of day 1, working at the end of day 2, working at the end of day 3, day 4, and breaks down on day 5. Okay, so we've just got to fill in the numbers now. That's a 1. Working, giving, working for 1, 2, 3, 4 would be 4 lots of 0.9. And then the last one is a broken, given, working, which was 0.1. Yes, what does that come to? 0.0656. Okay, Markov chain run length 4. And again, the outcome of part B is not dramatically different from part A, which was 0.0226. So, run lengths of opposing events in Markov chains are not necessarily all that different from each other, as distinct from Bernoulli run lengths of high probability and low probability events, which usually are dramatically different for a given run length. Alright, well, thumbs up to you guys. That's it. That's the end of this little session. I hope you had some fun. Thank you for coming. All the best to you, and go and do plenty of practice, okay? And we'll see you soon.